Good morning, everyone. It's my pleasure to give a contributed talk. I'm Wang from University of Science and Technology of China. Today, I would like to present thin-field QKD over 833.8 km fiber, mainly about my recent Nature Photonics paper. For all end-to-end QKD, without repeaters, there is a fundamental limit. While thin-field QKD built up a promising rate distance relationship to overcome this fundamental limit. In 2019, four groups first demonstrated the feasibility of thin-field QKD. We are the first one over fiber channel and get 2 kbps cycle key rate over 300 kilometer fibers. After this, the goal of twin field is to double the transmission distance of BB at 4, from 400 km to 800 km, and the corresponding tolerant channel loss from 70 dB to 140 dB. Just as the formula shown, we want to demonstrate the great potential of twin-field QKD. So my presentation will cover the following aspects: preparations of the fiber and the single-phone detectors, then the low-noise repeater-like source, and the measurement and compensation of phase drift. Finally, our result and conclusion. First, the optical fiber is the ultra-low loss one. The superconducting single-phone detector has a close 60% efficiency with 0.13 Hz dark count rate, which are in the same level of the one used in 421 kilometers BB4 experiment. This is the typical structure of twin-field QKD. The differential phase fluctuations can be written as this, which leads to two main experimental challenges. One is making the field generated by Alice and Bob twin, which means the frequency difference should be nearly constant. The other challenge comes from the phase drift accumulate over fiber channels. We need to compensate this fast phase drift to make delta NL equals to 0. This is our twin-field QKD system. The common ladder is free running, and its net is split into two parts, which are sent to Alice and Bob. The fiber used to transmitting the common ladder light is called server channel, and the continuous local ladder belonged to Alice and Bob. It's also split into two parts. One part interferes with the received light from the common ladder to lock the central wavelength. The other part is directly passed through the chopper, encoder, and the regulator, then passing through quantum channel. Finally, Alice and Bob's encoded twin field interfere on Chinese beam splitter and are detected by two superconducting single-phone detectors. As a core part, the repeat neck source is based on home-down optical phase lock loop. Through cloning the phase of the remote common laser, the wavelength difference between the local laser and the remote laser is substantially zero. We also added a negative feedback phase modulator to further reduce the residual phase noise. One important feature of the source is its high sensitivity. It can work very well with only 0.2 nanowatt input power, so the repeat neck source can work without the lead assistance of optical amplifiers, which would inevitably bring extra noise. This is a remote common laser and a local laser used in the experiment. Here, we first test the source noise without fiber channels. With 1 nanowatt input power, two sources, Alice and Bob, are locked to a common laser, and their corresponding output beams interfere on the beam splitter. The left one are the recorded interference outcomes over 400 seconds. The right are the corresponding standard deviation of phase drift, which are used to characterize the source noise. Figure A is the interference of two night beam from single laser. Figure C is the interference outcomes of two phase-locked lasers, but without the feedback PM. Obviously, they are similar, but the noise level of this source is still 2.5 times that of a single laser. Then, after the feedback phase modulator was added in the source, the noise level almost identical to that of a single laser. While without fiber channels, the noise of the interfere outcome mainly comes from the source, while after inserting long-distance server fiber channels, the repeater neck source was sensitive enough without introducing optical amplifiers. Thus, twin field could be remotely generated with very high quantity, almost perfectly. Compared with other source scans, such as the city laser and the scan locked to ultra-stable cavity, the noise in our repeater neck source is the lowest. We then use this up to characterize the phase drift of our whole system. The measurement setup could be seen as a large magenta interferometer whose arms consist of server channel and quantum channels, In either arm, the repeat next source collects the server channel and the corresponding quantum channel together. Here, all elements that would introduce phase drift are included. The laser source fiber channels, including server and quantum channels, the total fiber length is up to 1,689 kilometers. One difficulty of this measurement is the power of the interference outcome is very low, only a few nanowatt. We made a high-sensitivity detector based on APD, which is usually used for single-phone detection. The model is BGA 400 from PrinceNet Wave. The detector is operated at linear mode and close to minus 20 degrees centigrade. Its sensitivity is less than 5 picowatt with a bandwidth of larger than 100 kHz. The output was finally recorded by an oscilloscope with a 4 microsecond acquisition time. The interference fringe is indiscernible on a second time scale. Taking the data from the 10th second with 200 microseconds, well, the maximum drifted phase between two adjacent points was up to 0.172 radian, equivalent to 43 radian per millisecond. The standard deviation of phase drift rate over this 20 seconds is 14.47 radian per millisecond. To compensate the fast phase drift, we choose a frame period of 20 microseconds. This is a time sequence. The pulse string was chopped into bright reference part and weak quantum part. The intensity of the reference part is about 100 photons per pulse. At Chinese site, quadrature interference and in-phase interference were produced by adding half pi and 0 phase respectively. Thus, there are two effective regions in the reference part. The estimation range is used to estimate the value of relative phase drift phase. The phase indicator region is used to indicate the compensated result by showing the visibility of interference. Others are transition regions. In different scenarios, the view scenario and the fiber scenario, the duration of estimation region and quantum part were different, corresponding to different effective rate. As an essential part of a twin-field QKD system, stronger reference pulses would lead to higher visibility interference. The phase drift become quite intense at a long fiber channel. So we need more count of reference pulses. But count of reference decrease exponentially with fiber length. Thus, the intensity is stronger the better. Well, MPI noise caused by multiple discrete reflections of strong reference pulses would interfere with the quantum process and create additional errors. The source of MPI loss include double relay backscattering, splicing and collecting reflections combined with the single relay backscattering. Also include double reflections. The SNR requires the weaker the better. So there is a trade-off of intensity of reference process. Over 833.8 kilometer transmission distance, we measure the visibility of in-phase interference in the reference part and the MPI noise in the quantum part over different intensities of reference process, as shown in this figure. MPI noise increase linearly with the intensity of reference process. The visibility of reference first increase rapidly and then gradually. When the intensity of reference process varied from 40 photons to 240 photons per pulse, we choose here. The intensity with 115 photons per pulse. The corresponding visibility was more than 96%, and MPI loss is about 1 times of Dark-On rate. These four figures shows the stability of the system over different fiber lengths, 500, 600, 700, and 800, including the visibility of reference process, quantum bit average of a quantum process with respect of Chen. Each dot corresponds to the data gathered in 100 seconds. The inset are the corresponding distribution of the interference visibility of reference process and Qcrypt of quantum part. The total number of transmitted quantum signals for all fiber lengths was 3.2 10 to the power of 14 for different effective rates. The longest time was up to 200,000 seconds, about 56 hours. Finally, I would like to make a conclusion with this presentation. Here, we present an optimized thin-field QKD setup that could tolerate a channel loss beyond 140 dB and obtain a cycle distance of 833.8 km without the assistance of optical amplifiers. The cycle K rate substantially exceeds previous experiment. For instance, at 500 kilometers, that is more than 2 orders of magnitude than previous record. Our result not only demonstrates the great potential of thin-field QKD, but also provide a conceivable approach toward 1,000 kilometer fiber-based quantum K distribution. Okay, thank you very much for your kind attention. If you want to know more details, you can find them in this paper and its supplementary information. If you have any questions, I would be happy to answer it.